All right, everybody, welcome to the video for lesson number 8. I promise not to take too much of your time with this video because there's a lot of good stuff in this lesson, but there's also a lot of stuff that we're going to kind of retouch on from previous lessons and also in lesson number 9. So I basically want to just get through the main focus of what we need to get out of lesson 8. And by doing that, we're actually going to skip the opening exploration. So there's this cute little app online that allows us to pick fish from a river, and we can create a sample length of sample mean of their lengths. We don't need to do it together this way. It's just more of a way of us just seeing what sample means are yet again. So basically, from the opening exploration, all you need to take from it is if I take a sample of something, I can take that sample's proportion that's bigger or smaller than a certain value. Or in this case, I could take a sample, say, of 20 fish and measure all of their lengths and find the average length of the sample. So there is a difference between a proportion and a mean when we're talking about a sample. On the bottom of the first page, it says, when we create a sampling distribution for a sample mean from a given population, the central limit tells us what? So it tells us the population mean is within the normal distribution of the sample mean. Basically telling us that if we know what the sample mean is and we've taken a good representative randomly selected sample, that sample mean should be close to the population mean. So if I was to look around the classroom right now and ask everybody in the classroom what their shoe size was, and I found the average shoe size of the students in my 4th period Algebra 2 class, I then can take that mean of the sample of students at Cornwall Central High School and say whatever that sample mean was, say it came out to be 9.5 for average shoe size, I can say for Cornwall Central High School the average shoe size is probably also 9.5. Within an acceptable margin of error, which is what we'll talk about actually in tomorrow's lesson. For today, we're just seeing what a normal distribution looks like when we're talking about sample means. So here's some examples of 3 distributions that are shown, right? So all of our distributions now on the bottom, instead of being little decimals that are representing proportions, these are the actual means. Remembering each dot is a sample mean, so this would be a sample with an average or a mean of 125. So this might be whatever it is, SAT score or something like that. It doesn't matter. So as we look at these different samples, there's all kinds of different samples here. Some have more samples, some have less samples, some have smaller standard deviations, bigger standard deviations. The biggest thing from page 32 is that we can look at this and we can see this is a sampling distribution, not of proportions, but of the actual means of the samples because the numbers on the bottom are outside of the range of 0 to 1. And we're going to skip all of page 33 and go right to page 34. This is the big time question for this lesson. If we can get through this and we understand everything on this page, we truly understand what we need to know from lesson 8. Again, like I said, I don't want to waste your time. So number 5 says, researchers have questioned whether the traditional value of 98.6 degrees Fahrenheit is correct for the typical body temperature of a healthy adult. So to do this, these researchers randomly select 10 healthy adults and calculate their temperature. The sample is shown below. So these 10 numbers represent the 10 different people's body temperatures, creating a sample of people that are healthy humans. So we want to create the mean or the sample mean of the temperature. Sample mean, the symbol for that, remember, is X bar. And to do this, we're going to go back into our Algebra 1 brains, which we might not remember or might not have ever been taught this technique. but we can actually put all of this data into our calculator, and the calculator will do a lot of this for us. Because in the next lesson, we'll actually need to find standard deviations, which we'll be able to find in the calculator as well. So, in your calculator, let me just scroll this over so I could see all of the numbers. And let's see. Okay, so good. So in our calculator, to find this menu, we're going to hit Stat. I'll leave it highlighted red for a second. I'm then going to click Edit because I want to put these 10 numbers in my calculator. Now, you might have some junk in there from when you were doing this in Algebra 1 or something else that we even maybe did this year. I learned a cool trick the other day. If you have the new calculator, if you highlight the L2 or the L1 and hit Clear, and then go down, it actually clears the list for you. One of my accelerated kids showed me that little trick. I did not know that happened. Or you could go through and delete all of your data in there if you have the older calculator. Now what we need to do is type in all 10 of my temperatures. 97.73, I'm not going to say them all. I'm just going to type them in. If you want to even pause the video and type yours in, you can. I will say when you are typing in data, make sure that you go slow, double check what you did, because if one number is wrong here, everything about your problem is going to be wrong. And since we had 10 people in this study, there should be 10 pieces of data, which there are. Let me just double check my numbers. 7, 2, 7, 6, 8, 9, 5, 2, 7, 4, 7. Good. All right, so to actually calculate some of our data that we want here, we're going to go second quit to get back to our main screen, and we're going to hit Stat again. But this time, instead of editing, I want to put some calculations into place. So I'm going to go over to the Calculate menu. You might remember this menu from Algebra 1. We did some regressions, or we will do some regressions from this menu. We're going to get used to this menu for sure in the next week or so. But for today, we're just going to use what's called one-var stats. So we're going to hit Enter for option 1. And you're going to have options here. It's going to say list, frequency list, and calculate. If you have the old calculator, it's not going to say any of this. You just have to hit Enter. So if you have the new calculator, you want to make sure there's nothing in your frequency list because we don't have frequencies here. We just have single pieces of data. And then we're going to go down to Calculate and hit Enter. And it's going to give us an average temperature. See that first line says X bar, 98.784. So we'll say 98.8. So what we're seeing from the calculator is an average of 98.8. So it says if you were to take another random sample of 10 humans, would you expect to get the same value for the sample mean? The answer to that is actually yes, right? Or a sample mean relatively close to 98.8. Because remember, if we take a good representative sample that's randomly selected, whatever this temperature is that we got, we're assuming is the temperature also for the entire population of healthy adults. So if we were to take another random sample, we should be somewhat close to 98.8. So what we can do with this sample mean, just like we did with our sample proportions, is we can create what's called a dot plot. So we can computer simulate sampling 10 humans and measuring their temperatures, finding the average of that group of people, and figuring out what the range of data might actually be. And that's what I've done for you below. So below is a dot plot representing samples of 10 people and measuring their temperature and finding the average of those 10 people's temperatures. And we can see how the data is kind of spread. So it says, based on the dot plot above, if you were to take a different random sample from the population, would you be surprised if you got a sample mean of 98.8 or greater? So here's 98.8 or greater. We have to figure out how many dots there are there in that 98.8 or greater. So we're saying basically, what's the chance of our sample mean being greater than or equal to 98.8? Well, we know that there's 100 samples here because it tells us there's 100 different random samples, meaning there's 100 dots. And if we quickly count up those numbers that I boxed in for you, I got 28. I'm hoping I did not count wrong, but if I did, just correct me. Meaning there's a 28% chance of getting a temperature of 98.8 or more. So would I be surprised by this? No. This is a usual result. 98.8 is within the realm of plausibility, right? So we would consider this a plausible result, 98.8. So our answer up here of 98.8 is telling us, well, that's expected. I'm expecting that to be my answer. The next question said, would you consider a sample of 98 flat to be usual or unusual? So here's 98. So the probability of getting a temperature or an average temperature that's less than or equal to 98 degrees is only 2 samples out of the 100. So there's only a 2% chance of that happening. So this would be an unusual result. It's outside of the plausible area. If you look at where the bulk of all of the dots are, 98 is not even close to it. So this would be an outlier, we could call it. We could talk about this being outside of the margin of error, which is how we'll kind of assess this mathematically in the next lesson. The last question, and probably one of the most useful things about lesson number 6, is what happens if the sample size was increased from 10 people that we surveyed to 40 people that we surveyed. So one of the things that we went through kind of like a flow chart the other day of what happens when the sample size changes. So if the sample size is increased to 40, this is going to tell us the standard deviation will decrease, which tells us the margin of error will decrease, which will also tell us the confidence interval will spread less, getting closer to the actual population mean. Now, if we increase the sample size from 10 to 40, what happens to the mean of the sample? We can say the sample mean will get closer to the true population mean. So if I increase the sample size from 10 to 40, from 40 to 50, from 50 to 1,000 people, each time I increase the sample size, I'm going to get closer to the population mean because my sample is getting closer to the size of the population. There's no homework assignment assigned for this, so if you have some extra time at the end of this period, which I'm assuming that you will, you can go back and work on old homework assignments. You can work on the Regents Review assignment that the subs should have handed out to you, and I'm hoping that this all made sense. I'll see you soon.